Biology, Example 6, Rate of Growth of a Population. Let n equal f of t be the number of individuals in an animal or plant population at time t. The change in the population size between the times t is equal to t1 and t is equal to t2 is the change in n, which is equal to f of t2 minus f of t1. And so the average rate of growth during the time period where t is in between t1 and t2 inclusive is the following. The average rate of growth is equal to the change in n over the change in t, which is equal to f of t2 minus f of t1 divided by t2 minus t1. Now the instantaneous rate of growth is obtained from this average rate of growth by letting the time period change of t approach 0. So the growth rate is equal to the limit as the change in t approaches 0 of the change in n divided by the change in t, which is equal to the derivative of n with respect to t. Now, strictly speaking, this is not quite accurate because the actual graph of a population function n is equal to f of t would be a step function that is discontinuous whenever a birth or death occurs, and therefore not differentiable. However, for a large animal or plant population, we can replace the graph by a smooth approximating curve as in this figure. This is a smooth curve approximating a growth function. So instead of using a step function, we can then use this curve. Now, to be more specific, we're going to consider a population of bacteria in a homogeneous nutrient medium. So suppose that by sampling the population at certain intervals, it is determined that the population doubles every hour. If the initial population is n subscript 0 and the time is measured in hours, then we would have the following. We would say that f of 1 is equal to 2 times f of 0, which is equal to 2 times the initial. And then if we want to find f of 2, then that's going to equal 2 times f of 1, which then becomes 2 squared times n, or the initial. And then if we want to find f of 3, then that's going to be equal 2 times f of 2, which then becomes 2 cubed times the initial. So therefore, if we wanted to write this as a function of time, we would say that f of t is going to equal 2 to the t times the initial population. So we can say that the population function would be the following. So the population function n is going to equal the initial population times 2 to the power of t. Now remember that whenever we have a variable in an exponent, then what we can use is logarithms. So remember that in section 3.4 we showed that the derivative with respect to x of our exponential function was equal to a to the x times the natural log of a. So we can say that the rate of growth of the bacteria population at time t would be the following. We would then say that d, the derivative of n with respect to t, is then equal to d of t of our initial population times 2 to the power of t. And so we know that that's going to be the value of the initial population of 2t times the natural log of 2. So therefore, there is our derivative formula. So, for example, suppose that we start with an initial population of 100 bacteria. Then the rate of growth after 4 hours is going to be the following. Well, that means that we know what our values are. We know that from our given information, we know that the initial is equal to 100, and we know that t is equal to 4. And then we're going to plug it into the formula dn of dt, which is equal to the initial population times 2 to the t times the natural log of 2. So let's go ahead and plug that in. So it's going to equal 100 times 2 to the 4th power times the natural log of 2, which becomes 1600 times the natural log of 2, which gives us approximately 1109. So this means that after 4 hours, the bacteria population is growing at a rate of about 1109 bacteria per hour.